And the next speaker is Pieter de Frenne from the Forest and Nature Lab at Ghent University in Belgium. Thank you, Pieter.
Thank you very much, Emmanuel, and thank you for coming to this symposium. So I will now talk about the forestREplot database, which is a database of forest understory herb layer, but also tree and shrub layer data, in which Don's data that he now presented from Wisconsin are also included. So I will mostly talk about, or only talk about, the temperate forest area in this presentation. So this is the distribution of temperate forests across the globe, and this is not the largest part of the global forest area, only 16% of our forests, but these forests are of course situated in some of the most densely populated parts of the globe, and as a result they are prone to a lot of human influences, anthropogenic global change drivers. But on the other hand, of course, they are also very valuable for biodiversity conservation because they are in parts of the world where there is not much forest left. And so this is also clearly shown by this report by the IPBES in 2018, showing that the temperate and boreal forests in Europe and Central Asia are here at the top. And what they show is that, and many others have shown, that land use, climate change, invasive alien species, and pollution mainly due to nitrogen and sulfur, and wood extraction are the key drivers of biodiversity change. The forestREplot database is focused on the herb layer, but also includes data on the tree and the shrub layer. So the definitions that we and that many other forest ecologists use to distinguish these layers and to do a vegetation survey are a bit different than in grasslands, for instance, or in heathlands, where this vertical complexity is a bit different. And so when doing vegetation surveys in forests, we usually do a separate survey for the herb layer, which are all vascular plants, including seedlings, saplings of trees and shrubs, smaller than 1 meter. Then we do a separate survey in the shrub layer between 1 and 7 meters, and then all trees, usually only trees, only plants that are the only plants that are taller than 7 meters are done in a third survey above 7 meters. So why a focus on this herb layer? First of all, because as you probably know, in temperate forests, the majority of plant biodiversity is not in this tree layer, but in the herb layer. So on average, 80, sometimes 90, or more than 90% of the total plant biodiversity is in the herb layer, and only a very small proportion of the species present, of the plant species present, are trees in the tree layer. And so for biodiversity, this is a super important layer in temperate forests, but also for the functioning of the forest. It's a very important layer. It's often neglected, and people, for carbon stocks or evapotranspiration or climate impacts mitigation, people only look at the trees, this herb layer should not be neglected also for ecosystem functioning of the total forest. And so we have synthesized this recently in a meta-analysis where we looked at the impact of the herb layer versus the total forest functioning of the productivity, the nutrient cycling, evapotranspiration, and tree regeneration. And what we saw was that, for instance, for productivity, the herb layer accounts for 10 to, in some cases, 40% of the total forest productivity. Nutrient cycling at the nitrogen, potassium, magnesium concentration of leaves in the herb layer is a factor 2, 3, 4 higher than in the trees. Evapotranspiration can also be significantly influenced by the herb layer, especially in open forests, where it can contribute 30 to 40% of the total forest evaporation. And then, of course, the herb layer, that's the place where the young trees are growing. So competition between the herbs and the trees is there taking place. And so usually presence of a lot of understory herb cover results in lower regeneration. Good, so we do forest resurveys, so this means that these are repeated surveys from a vegetation plot at the same time, and so often it can be a challenge to find back the exact location, and so we rely on a good description of the previous survey, and so we rely on very well descriptions of what has been done in the past, how the plot was located, usually relying on old big trees to relocate the plot or other features in the landscape, like small creeks or particular topography. And then we go back to the same place and resurvey. In some cases, plots in our database are also permanently marked in the field with sticks like here, or with irons in the ground or something, or with paint on trees. So then, of course, the relocation error is smaller. So also the tree and the shrub layer is then again surveyed, of course, to take into account in the analyses. I included this slide to also attract your attention to the fact that in many of the, even though that many of the analyses that I will now show and the results that I will show focus on the herb layer, for especially to look for the drivers that have caused these changes, we really rely on this tree and shrub layer. Also, for instance, to calculate how the microclimate has changed or the light environment has changed or the quality of the litter. We really rely on this presence of data about trees and shrubs also in the past. Good, and the importance of resurveys becomes clearer when you have more plots across a larger geographic area, of course. So this is one of the strengths of forestREplot, I think, that we combine different data from different regions, plots from different regions, where we can then calculate some community change over time, and then relate this to environmental drivers. And here we plotted canopy, changing canopy openness and changing temperature. So by combining plots from different regions across a large geographic area, these environmental drivers are not changing in the same way in all places. And by combining them, you can increase the orthogonality of the design. So especially resurveys that are done in multi-regions, the black line here score then quite well on various characteristics, such as the representativeness, which questions or how do they represent what is happening in reality, the comprehensiveness, which questions you can address with that study, and then also the orthogonality, are we able to disentangle effects of nitrogen from climate change, for instance. Good, so the current status of forestREplot is this. So at the moment we have 5,500 plots, resurveyed plots in the database, so they are permanent or semi-permanent. 500 from Eastern North America and 5,000 from Europe. The baseline survey, or the median time interval between the two time steps is 4 decades. But this is quite variable, as you can see here on this graph, with the baseline survey timing in red and the resurvey in blue. So the average baseline survey was done in the 1960s, more or less, but we have vegetation surveys going back as early as 1933. And then the average resurvey was done in the 2010s, but we have resurveys as recent as last year. The forest type that is in the database is lowland forest, so we don't have very high elevations in Europe and also not in North America. The plots are mostly quite large, so somewhere between 10 by 10 meters and 20 by 20 meters in most cases. And most of the plots are also in ancient forest. This is logical because they are, in most cases, most important for biodiversity conservation, most species rich. And so the ancient forests are not primary forests or old growth forests, so they definitely may have been managed. But ancient means that they have never been converted to another land use than forest. So they have never been converted to arable land, for instance, or grassland. As long as we can go back in time with the records that we have, so which is in most cases about 300 years. So the management committee is, I'm part of the management committee, and Don is also a part of the management committee. So we manage the forestREplot database with 4 institutions in Belgium, in Wisconsin, in Jena in Germany, and in Brno in the Czech Republic. So maybe there are also people here in the audience that now think, I also have some forest survey data. So you're very welcome to submit them to the database. So the criteria that we need are listed on our website. So most importantly, we need about 20 plots per region, and the minimum intercensus interval should be 20 years. And for the rest, I explained these criteria, so don't hesitate to contact us in case you think that you have suitable data, especially in regions where we don't have any plots yet. Good, so that's the status of the database and why it's important. So now I will continue my presentation with some key results that we have been able to discover with this database. So we established the database with the first paper in 2012, so 12 years ago. And so in the past 12 years, we have looked at various drivers, climate change, nitrogen deposition, but also at various properties of the vegetation, from species richness to composition and other things. So the first paper that we started with was focused on simple species richness changes over time in different regions, only in Europe. And here I plotted the change in the species richness as a log response ratio. 0 is no change. And what you see here is that basically some regions go up, other regions go down. So the cross-region mean is centered on 0. But there is a lot of variation. And we also did not find any clear effects here with this analysis on species richness of nitrogen deposition, for instance, or climate changes between the 2 surveys. But then we looked a bit more first into the effects of nitrogen deposition on these forests that we have in the database, also adding a bit more regions also where there was low nitrogen deposition, because in this first paper, many of the regions were coming from regions with high nitrogen deposition. And as expected, we then found a signal of nitrogen deposition because, of course, this is what I here plotted, the shifting baselines. So if the baseline survey is coming from a region with very low or very high nitrogen deposition already present at the baseline survey, then of course it's logical that the shift that you find after that point in time is quite low. And so by adding also data from regions with low nitrogen deposition at the baseline survey, we found that the higher this cumulative nitrogen deposition between the 2 points in time, the more negative or the higher the species loss was. In addition to species richness, we also looked at some particular species groups. Don already referred to it with Parthenocissus. In Europe, we also have shown this. And this is a phenomenon well documented in the tropics, is that there is lianification. So that there are more and more lianas, as Don mentioned, particularly due to enhanced atmospheric CO2 concentrations. Of course, in Europe, we don't have so many lianas, so we focused this paper on 3 liana species. And the outcome is plotted here with the frequency of the lianas in the baseline survey in blue and in the resurvey in red. And you see that for almost all regions, the liana cover is increasing over time. And this pattern is almost entirely driven by one species, by Hedera helix. Then we also looked at the regeneration, just as Don has shown for Wisconsin. There are quite a lot of changes going on in with regards to the trees present in the herb layer. So in this particular paper, we looked at the temperatures that the juvenile trees, so the small tree saplings, are experiencing compared to the adults, and this in the 2 time periods. So what we plotted here for 26 species, if I remember well, 26 very common species in European forests. We plotted here the difference of the temperature. So the temperature difference between what an adult tree experiences above the canopy, so in the air, in the free atmosphere, and the temperature that a young tree regenerating in the herb layer is experiencing. And so this is always positive. It's logical. There is microclimate buffering at the forest floors. It's cooler. So in most cases, the adult is experiencing warmer conditions than the juveniles. But we also see that this difference between the adult and the juveniles is increasing over time. So the red is the baseline, and the orange is the resurvey. And you see that for almost all species, and this is significant for 8 out of the studied species, for almost all species, this difference increases over time. So this means that the temperature difference between what an adult tree experiences and a young tree of the same species experience is increasing as a result of climate change, but also as a result of changed canopy cover, which makes that the forest floor in forests that became denser over time is cooling a little bit, and the young trees experience cooler temperatures. Good, so if we then go back to nitrogen deposition, we digged a bit deeper to see which species suffer most from nitrogen deposition. And it seems that these are the species that have a very small distribution range. And so we plotted the range size in square kilometers here on the x-axis and the probability of extinction of that species on the y-axis. And we see that for regions where there is very low cumulative nitrogen deposition between the baseline and the resurvey, that this is not important at all. But in regions where there is a lot of nitrogen added between the first and the second time point, then this range size is becoming more and more important, and we see that species with small ranges, they have the highest probability of extinction, whereas common species, generalist species with a large distribution range, their probability of extinction is not different than in a region with low nitrogen deposition. And then to make things even more complex, also coming back to Don's story about the white-tailed deer can also change this pattern. So here on the x-axis, we plotted the herbivory pressure. So how many more deer or less deer are there in that particular forest? And first focusing on the high nitrogen deposition regions, we see that, for instance, the percentage of red-listed species declines with herbivory. The percentage of small-ranged species declines with herbivory. And so this is probably because when there are a lot of deer, they browse on the shrubs, on the other plants in the herb layer. They provide more light to the understory, and as a result, then plants can can profit from this enhanced nitrogen availability and outcompete rarer species. Whereas this pattern is entirely reversed in regions with low nitrogen deposition. And then you see that herbivores and higher deer densities can even be positive. So because of this higher light availability, they actually make niches, they provide opportunities with higher light patches for small-range species and for red-listed species. Okay, so I already started the first slide about the results. I explained that basically the changes in species richness between the first and the second survey are centered on 0. This is confirmed here on top, where we again plotted the diversity change value for taxonomic richness, for instance, between 0.1 and 0.2. But now we recently also did an analysis to look at functional diversity metrics, here in red, and phylogenetic diversity to see, are these changing also or more than only taxonomic richness? But it seems that overall, when you just average out all plots, also these metrics are centered on 0. And so it's not that overall, across all these quite mature, quite healthy forests, at least compared to conifer plantations, for instance, this diversity change is centered on 0. But of course, there are some directional changes taking place. In addition to nitrogen deposition, we focused especially also on climate warming impacts. And so one way to quantify this is to look at thermophilization. So thermophilization is a method to quantify how much warm-adapted species there are in the community. And so overall, you see the average of these lines is above 0, so there is an increasing dominance of warm-adapted species. But then it's especially at a local scale, the forest canopy cover that is regulating the local dynamics. And so what we saw was that in forests that became denser over time, that there the thermophilization is quite close to 0. Whereas in forests that became more open over time, there the thermophilization is significantly stronger and more positive than in forests that became denser over time. And this is clearly caused by microclimate change. So in a follow-up paper, we then, in a subset of the plots, we installed temperature sensors for 1 year, monitored microclimate with an I, and related this to the canopy cover such that we could calculate back the microclimate to 70 or 40 years ago. And this is what is plotted here on the x-axis, the change in the temperature over this time period, but taking the microclimate into account, so taking the canopy cover change into account. If you use weather station data, the slope is 0. So it's not that regions that have to warm more, according to weather stations, experience more thermophilization, but it's again the plots that have warmed more than the macroclimate. So these are forests that became more open over time. Those have warmed more than a weather station. There we find strong increasing dominance of warm-adapted plants. And in forests that became denser over time, there the temperatures might even have cooled because of densification of the canopy and a compensation of the warming that is found outside in weather stations. Good final result to make a link with pollinators is that we also recently quantified the change in the potential nectar production, so using literature data of how many nectar and sugar each plant species is producing on average, and then calculating this for the baseline and the recent survey, we calculated the change per year or within a year in the potential sugar supply. And what we found was that, this of course changes a little bit in the year, but across the year, the potential sugar supply declined by 1/4, more or less. So because of changes in abundance of species and how much sugar and nectar or sugar there is in the nectar. Good, so the potential implications for pollinators will depend, of course. This light availability, canopy opening, microclimate will, of course, have a big impact and might have a positive impact if canopies become more open, might also result in more flowering of forest plants. But on the other hand, we showed that the species that produce a lot of nectar, they declined. So we see this 24% decline in potential nectar production. And maybe also this phylogenetic diversity, even though it's centered on 0, we have to see whether and which species that are important for pollination services, how they have changed over time. So the way forward, very briefly, in 1 minute, is that we aim to fill regional gaps in the database, so especially data from western and southwestern France, North Spain, North Italy, for instance, Greece, the Balkan area, the temperate parts of those countries are very welcome to submit additional data. And so then there are two major projects in which we will use the forestREplot database in future research. First, an ERC consolidator grant that is starting now will focus on how novel light regimes are impacting the understory, because as a result of drought, many trees are now losing their leaves in the summer already, creating a lot of light at moments when previously it was a quite dark forest. And then secondly, there is a biodiversa project that is starting, where we are, that is particularly directed to inform policy and how forest biodiversity in Europe has been changing, where we will calculate essential biodiversity variables to see what is the current status of forest biodiversity in Europe is. So, thank you very much for your attention.